Today we're going to take a look at rational exponents. So remember that a rational number is essentially just a fraction. That's what we mean when we say rational number. We mean something that can be represented as a fraction. So an example of a rational number might be 2/3 or 1/2. So far we've only looked at what we call integer exponents, whole number, positive or negative exponents. Today we're going to talk about when our exponents are fractions, when our exponents are rationals. The same exponent rules that we've used so far still apply. So we're using all the same rules. If I take a look at example A, I've got 5 to the 1/2 power times 5 to the 1/4 power. Up to this point, most of what we worked with have been variables for our base. So if you wanted to start, we can think of this as x to the 1/2 power times x to the 1/4 power. I would treat this exactly the same way if I had x to the second and x to the fourth. So for a problem like this, we would combine by adding the exponents. We would do the same if it was x to the 1/2 and x to the 1/4. The difference is that we'd have to get a common denominator first. So 1/2 would be 2/4. So this would give me x to the 3/4. Now let's hop back to example A, where I've got 5 to the 1/2 and 5 to the 1/4. I'm going to treat this exactly the same way. I'm just going to add those exponents. I'm multiplying numbers that have the same base. It doesn't matter what that base is. I'm multiplying numbers that have the same base. So we're going to add their exponents. So I need to add 1/2 and 1/4. That means I need common denominators. So this would be 2/4 plus 1/4. That would give me 3/4 for my exponent. So this would be 5 to the 3/4 power. For B, we're going to treat this the same way we would treat it if I had an A and a B here. So I'm going to use A and B for now, and then we'll go back to the 8 and the 5 towards the end. Distribute my outside exponent inside those parentheses. So I would get A to the 1/2 times 2 times B to the 1/3 times 2. 1/2 times 2 would be 1. So this would be A to the first. 1/3 times 2 would be 2/3. So this would be B to the 2/3. Now I'm going to substitute back in what I had originally, which was 8 and 5. So this would be 8 to the first, or just 8, times 5 to the 2/3. Notice that I'm not multiplying 8 and 5. I don't actually have 5 here. I have 5 to the 2/3 power, whatever that is. So I don't want to do anything different than I would if this were A and B. For C, we've got a negative exponent here. So I'm going to start by moving this to the other part of our fraction. This would all be over 1. I'm going to move this to the bottom. So now I would have 1 over 2 to the 4th times 3 to the 4th, all to the 1/4 power. I'm going to go ahead and distribute in that exponent. So this would be 1 over 2 to the 4 times 1/4 times 3 to the 4 times 1/4. So this would be 4 times 1/4 is 1, and 4 times 1/4 is 1. So my simplified expression here would be 1 over 2 to the first times 3 to the first. Now, in this case, I can go ahead and multiply 2 times 3. I have 2 and I have 3. Here I didn't have 5, I had 5 to a goofy exponent. Since I just have 2 and 3 here, I can rewrite this as 1 over 6. For D, I've got 7 divided by 7 to the 1/3 power. Now, if this were x, let's say to the 5th divided by x squared, we know that we would subtract those powers. So big minus little, 5 minus 2 would give me 3. We would have x to the 3rd. It would stick on top because that bigger exponent is on top. I'm going to do this the same way with my base of 7. And I want you to remember that if I don't see an exponent, that means that it's 1. So what I'm going to do, since I'm dividing things that have the same base, is subtract the exponents. So I would do 1 minus a third, big minus little. 1 minus a third would give me 2/3, and it would stick on top because that's where the bigger exponent was. So I would have 7 to the 2/3 power. I'm using all of those same exponent rules that we've already discussed. Just now I'm using them with fractions, and in some cases I have bases that are numbers instead of variables. But the rules are the same. The rules have not changed. And let's look at our last example here, example E. I've got an exponent outside of parentheses, so I'm going to distribute that in. That would give me 12 to the 1/3 times 2 over 8 to the 1/3 times 2. So as I go to simplify my exponents, this would be the 2/3 power, and this would also be the 2/3 power. So I have 12 to the 2/3 power over 8 to the 2/3 power. So I've used all of my old exponent rules to do some simplifying here. The last thing I want to talk about is what does it mean when I have a fractional or a rational exponent? Okay, so if I have 4 to the 1/3 power, what does that mean if I were to try to evaluate or simplify that? So 4 to the 1/3 is actually a way that I can represent a root. This would be the cube root of 4 to the 1st. I could also represent this if I wanted with that exponent outside the root. In some cases, one version is easier to simplify than the other. But what I'm seeing here is the top, the numerator of that fraction, is the exponent, and the bottom is what we call the index for the root. It tells us what type of root we have. So what I'm saying here when I say 4 to the 1/3 power is I want the cube root of 4, or the cube root of 4 to the 1st. I can also take this the other way. So if I have a root, I can rewrite that as a rational exponent. So this would be 7. The power is the numerator, and the index for the root is the denominator. So this would be 7 to the 2/5 power. In some cases, being able to convert between that root expression or the power expression makes it easier to be able to simplify. So the last thing I want to do is actually go back and rewrite each of these in that alternate form. So 5 to the 3/4 power, I could also represent as the 4th root of 5 cubed. And again, in some cases, I'm going to want the power under the root. In some cases, it's easier to simplify with it outside. They are equivalent, they mean the same thing. For B, 8 is going to stay as 8, but 5 to the 2/3 power, I could represent as the cube root of 5 with the square under or outside of that root. For part C, we ended up with 1/6. So no roots or fractional exponents left there. I'm going to leave that as it is. 7 to the 2/3 power, I could represent as the cube root of 7 squared. If I want the exponent under the root, that's fine. Or the cube root of 7 with the square outside the root is also fine. And then for E, this would be the cube root of 12 squared. And then on the bottom, the cube root of 8 squared. Now, I could, if I wanted, again, put those squares under the roots, but I want you to notice that we know the cube root of 8. That's just 2. So on the bottom here, the cube root of 8 is 2. What I really have here is 2 squared. So the bottom of this becomes 4. That's why we want to be able to convert between these different forms, because what I may not recognize as something that I can simplify with that rational exponent, I can recognize how to simplify if I write it in root form instead. Now on top, 12 doesn't have a nice cube root. And if I wanted to simplify this, I would need 3 of something to be able to simplify that root. 12, I'll think of it as 4 times 3. 4 is 2 times 2. I've got a pair of 2's, but I would need 3 of them to come out here. So I'm not going to be able to simplify that at all. So I could leave that if I wanted as 12 to the 2/3 power, or I could leave it in that root form if I'd like. So rational exponents, fractional exponents have the same rules as integer exponents. If I have the same base, I add the exponents. When I'm multiplying, I subtract them. When I'm dividing, power to a power, I multiply. I can distribute those powers in just like we have with every other exponent that we've looked at. All of the rules are the same. The only new thing that I get is that I can convert between that root form and that rational exponent form.